Let's try to solve this problem here. So we have a parcel of mass 2 kg. So this is a parcel, then it has mass 2 kg. And now this parcel here is placed on a rough inclined plane. So I believe this is a rough inclined plane, as shown in the figure above. It is then released from rest. So initially it should be at rest. So if you want, you can state u equals 0 meter per second here. Okay, and then after that it accelerates at a constant rate of 4 meter per second square. So a over here should be equals to 4 meter per second square. Okay, then they ask you to determine the coefficient of kinetic friction for the parcel. Coefficient of kinetic friction, it's mu k. This is a Greek alphabet mu subscript k for kinetic. Okay, so most of the time when we deal with a chapter 4 question involving forces, the first step is always to draw a free body diagram to illustrate all the forces acting on the object. So in this case, our object of interest here will be this parcel of mass 2 kg. So let's draw the free body diagram. We start with a dot here to represent our parcel. Then we will need to draw our axis. Our axis will be inclined, or slightly rotated, because the plane where the object can possibly move it's this plane over here. So I have to incline our axis a little bit so that it's parallel to the plane where the motion can possibly happen. So this one you can label it as X. This one you can label it as Y. Okay. Then after you have done with your parcel, with your axis, you ask yourself the 5 questions. So the first question is whether this object has mass or not. Yes, it's a parcel, it should have mass. So the earth is beneath, so the weight should be pointing downwards. Next question, is it attached to any rope, strings, or cables of such? No, okay, you can't see any cables being attached to this parcel over here. Third question, any force being explicitly mentioned in the statement or in the diagram? Well, you see nothing, right? They didn't mention any force, any push or any pull or things like that. No, nothing being mentioned, so no external force. Fourth question, is this object touching any surface or touching any other object or not? Yes, as you can see here, this parcel here is touching this surface here, and this is the surface of the rough inclined plane. So you should expect there's a normal force. Okay, so if you're not sure how to determine the direction of normal force, please review a video on how to draw the free body diagram. But the main idea is it should be perpendicular to this plane over here. It should be perpendicular to this plane. So this one, this is the direction, either up or down. Use push to determine. So push will be this way. Okay, last question, is it a rough surface? Yes, you're touching a surface and this surface is rough. In this case, you have to determine whether the friction will be kinetic friction or static friction. But mentioned here is that it accelerates at a constant rate of 4 meters per second when it's released from rest. So it goes from not moving to moving. So this is a kind of moving, okay? So it's kinetic friction. So for this kinetic friction, to determine its direction, it has to be opposite the direction in which the object slides. So the object is sliding down the slope, so you should expect opposite direction, which is up the slope, will be the direction of kinetic friction. So this is your direction of kinetic friction. Okay, so you have finished, ask yourself the 5 questions. So technically you are done with your free body diagram. But of course you need to bring in the angle. So this 30° here, where should you fill in? You fill it in here. Okay, if you are still not sure why is it here, use something like this, something like this. Okay, your weight is pointing this way, right? So this one is 90, this one is 60. Then 90° over here, 90° over here. So this will be 30°. Okay, if you're not sure why, how do you get this 30°? Watch the previous example in Newton's first law. I think there they explain it. Okay, so we are done with our free body diagram. Now our task will be to determine the coefficient of kinetic friction. Strategically speaking, if you are asking something about friction, you might need to determine the kinetic friction first, right? And after getting the kinetic friction, only you relate to the coefficient of kinetic friction, which is your target. And how do you relate them together? You use kinetic friction is equals to coefficient of kinetic friction times the normal force. So in order to get this value over here, I believe you need to find the kinetic friction and you need to find the normal force. The normal force is happening in the y dimension, whereas the kinetic friction is happening in the x dimension. So I believe you need to analyze both dimensions in order to do this question over here. Okay, but before we move on to the x and y dimension, we see that the weight over here is not lying on the x-axis, nor is it lying on the y-axis. So in this case, since it is at an angle in between the x and y axis, we have to resolve it. So to resolve it, we break it into its x component, which is wx, and we break it into its y component as well, which is wy. So wx here can be found using opposite, because this is opposite, so it should be w sine 30 degree. Okay, whereas for this part wy can be found using w cos 30 degree. How do you get w cos 30 degree? Well, this is the angle, this is right adjacent to it, so adjacent you use cos. Okay, so now once we have resolved everything, we move on to study the situation here. Okay, so in this situation, we know that this object here will be sliding down this rough inclined plane over here. And our focus is we want to determine the kinetic friction, we want to determine the normal force. So let's try our luck with the x dimension first. Then if we are stuck, then we move on to the y dimension. Usually when we deal with chapter 4 questions, right, you usually need to analyze both dimensions. So you see which dimension is more probable to get the answer, then you try it first. Then once you get stuck, you switch to another dimension and solve the equation for that dimension. Then at the end, you get a simultaneous equation or such. Okay, so let's try. So let's do it for the x dimension first. Sum of fx. Okay, so should it be equals to 0 or should it be equals to ma? Should we use first law or should we use second law? So let's observe. In this situation here, we see that this object is accelerating down the slope. So in this case, there's an acceleration. If there's an acceleration, there must be a net force. So when there is a net force, how do you relate the net force and the acceleration is you use the Newton's second law. So in this case, you can use your Newton's second law to solve this problem. Okay, so once we are done with that, we can proceed by seeing what are the forces that are in the x direction or the x dimension. Okay, so you see here the forces that are in the x dimension are the kinetic friction and the x component of weight, but they are in opposite direction. So now you know that this object is accelerating in this way. It's accelerating this way. So the usual way of redoing chapter 4 question is we treat the direction where the acceleration is pointing, we treat that direction to be positive. So usually, in usual cases, our x and y is like this, right? This is the usual x and y. But because now our acceleration is pointing this way, therefore we will not follow this. Instead, we will change our positive x to be in this direction instead. Okay, y will later determine whether y should be up positive or down positive. But for now, the x should be along downwards the slope, we treat it as positive. Okay, so how should we write to mention that we are changing our positive and negative side? So what we do is we write for question number 1, we are taking down the slope as positive. So we are choosing down the slope as positive. So if your force is pointing in the direction down the slope, then that is a positive component. If your force is pointing up the slope, then that's the negative component. Okay, so in this case, if you look at this free body diagram, this x component of weight here is pointing down the slope. So we'll treat that as positive. Okay, so we'll write this one as positive, weight sine 30°. This one is positive. How about the other side? The other side we have the kinetic friction. Kinetic friction is up the slope. Up the slope is opposite this one, so it should be negative. So we'll take kinetic friction to be negative. Then it's equals to max. In this case, we will put our ax here has a positive value already. Ax here will contain a positive value, and the positive value will be 4. Okay, if you don't do taking down the slope as positive and you do it the conventional way, then your acceleration will be negative already, because the acceleration is in the usual negative x direction. So if you want to do it that way, you have to put your ax as negative. But now if I flip my axis, so that my x is in this, my positive x is in this direction, then I will allow this part to be positive, and I allow my kinetic friction to be negative because I flip my axis already. Then now, because my acceleration is pointing in this direction, therefore my acceleration here will be a positive value. Okay, it takes some practice. We are now flipping the axis. Okay, this is something new. Then with practice, you get better at it. Okay, so we continue. So right now, we are interested with the kinetic friction. So let's bring kinetic friction to one side. Then what you have on the another side is W sine theta sine 30° minus max. W is equals to mg. Let's straight away substitute 2 kg 9.81 sine 30° minus 2 kg. Your acceleration is 4.0 meter per second. So if you calculate that, I believe the answer you should get is 1.81 Newton. So that's the kinetic friction, the magnitude of the kinetic friction. And this kinetic friction here is pointing in the negative x direction. And where is our negative x direction? Our negative x direction is pointing up the slope. Okay, when you're doing this thing, right, I think I can encourage you all to remove this x over here, because we usually label x at the positive x side. So now if we flip our axis already, it's better not to label the x and y. Instead, we use these words over here to indicate whether where is positive, where is negative. Okay, so now we move on to question 2. We move on to the second part, the y dimension. We move on to the y dimension. So for y dimension, where should we treat as positive? Well, let's discuss. For the y dimension, sum of fy, let's see whether this object here needs to be analyzed using first law or second law. In this situation, this object here is accelerating down this inclined plane. But in the y dimension, you see the object never moves up or moves down, right? So technically, if you just focus on the y dimension, it is only at rest in the y dimension. Okay, it never move and never accelerate upwards, never accelerate downwards. It stays at rest in the y dimension. So if at rest in the y dimension, we'll analyze it using first law for the y dimension. So here we use first law. So first law tells us that sum of fy is equal to 0. Okay, so when sum of fy is equal to 0, it's not a must to define where is positive, where is negative, because you take one side minus the other side, you get 0. No matter you take down minus up or up minus down, you still get 0. So in this case, I can choose to take either taking n minus w cos theta, or I can take w cos theta minus n. Both are fine because the n answer will be equals to 0. So let me write n is equals to n minus w cos theta, cos 30° equals to 0. Then now n is equals to w cos theta, cos 30°. So now substitute. Okay, you can write mg cos theta, cos 30° first. So this will be 2.0, 9.81 cos 30°. And if you calculate all this, the answer that you should get is 17.0 Newton. Okay, so once you have gotten your kinetic friction and your normal, you can use this equation here to find your coefficient of kinetic friction. So let's do that over here because I'm a bit out of space. So taking Fk equals to mu k n. So Fk is 1.81 equals to mu k, the coefficient of kinetic friction, multiplied by 17.0, the normal force. Then you get your mu k equals to 0.106. So that is your coefficient of kinetic friction. Okay, again, the general strategy is to get your free body diagram well labeled first. And after that, if you have any force which is not lying on the x-axis or y-axis, you have to resolve it to its component, the x component, the y component. Then you focus on each dimension. In this case, you focus on the x dimension first, and we see that the x dimension is accelerating, so we use the second law to analyze it. So when we use second law, we take the direction of acceleration as the positive direction. So in this case, the object is accelerating down the slope, so I take down the slope as positive. So in this case, I take what is pointing down the slope, Wx, minus what is pointing opposite up the slope, Fk. So by doing this equals to ma, I flip around, I can get my Fk. Then I change my dimension to the y dimension. For y dimension, since it's at rest in the y dimension, we use the first law to analyze. Since it's first law, I take up minus down or down minus up, it doesn't matter. So I take up minus down, then I calculate, I get my answer. Then I use the equation Fk equals to mu kn. Then I find my coefficient of kinetic friction. So that's all for this question.